All right, in this video, I'm going to be looking at the review for the in-class test 4 that we're taking on Monday and Tuesday. So problem number 1 deals with trying to classify a triangle according to sides and angles. So if you're looking at classifying a triangle according to its sides, you have the option of scalene, isosceles, and equilateral. Equilateral means all the sides are the same, equal sides. Isosceles would be just 2 of them the same, but 1 different. And scalene is all 3 are different. All right, then in terms of angles, you have the option of acute, all less than 90. Right means you got a 90-degree angle. And then obtuse means there's a angle that's bigger than 90 degrees. So this first triangle, they didn't mark that the sides were the same and they don't appear to be, so that would be scalene. And none of the angles appear to be 90 or bigger, so that makes it an acute triangle. All right, this one's also acute, the second one. All the angles look like they're less than 90, but these 2 sides are the same, so that makes it isosceles. Okay. All right, now another triangle idea that you need to be familiar with is that all the angles would equal 180 degrees. So if you're trying to find a missing angle in a triangle and you have 2 angles given to you, you can add them. Then you know that the third angle would be whatever's left out of 180. So take 180 minus 145 and get that. This must be 35 degrees. Angle C must be 35 degrees. Okay. Now another important concept is the Pythagorean theorem. So the Pythagorean theorem says that in a right triangle, has to be a right triangle, okay, and the triangle is typically labeled using A's for the short sides and C's for the longer one. You know that A squared plus B squared equals C squared. Let me go ahead and draw the triangle that would go with that. Would be if you had a right triangle with the right angle labeled C, okay? So on this one, if I want to know this missing side on triangle A, that's the hypotenuse. So what I would set up is that 7.9 squared plus the 9.3 squared would have to equal the x squared. So the x squared would equal, and I'm going to go ahead and do the 7.9 squared plus 9.3 squared. Okay. Sometimes I just like to do it. I think I'll show you how to do it in one step. All right, so we know that x squared equals the 7.9 squared plus the 9.3 squared. But to not introduce round off error, a good thing to do is to go ahead now and do the square root of that. And you do want the positive square root. Okay, so what I can do is get the square root symbol on my calculator and then put in the 7.9, square that, plus the 9.3, make that squared, and all at once I'll get my answer. Okay, so I wound up with, let me make sure I did that right, square root of 7.9 squared, sorry I entered it wrong and I had to do it again, the 7.9 squared plus the 9.3 squared, okay? And I wound up with about 12.2, okay? So this would be, I'm running out of room and I can't get more paper right now, but I'll squeeze it in right there. That would be about 12.2. So this side would be about 12.2 centimeters. Now on the other one, when I go to set it up, I know that 14 squared plus b squared would have to equal the long side squared. And so the b squared would equal the 24 squared minus the 14 squared. And rather than introducing round off error, I'm going to go ahead and just type that in, the square root of all of that. Okay, so I'm going to go in and grab the square root sign, do 24 squared minus the 14 squared, and I wind up with 19.5 on that one. 19.5. So that means side B would be 19.5 miles, about 19.5 miles. So that's the Pythagorean theorem. Anytime you have two sides of a right triangle, you can get the third side using the Pythagorean theorem. All right, now let me go back to the original document for a moment. I need to take a picture of the next part I want to do, because this is a PDF, so I can't write on it like I do a Word document. So let's take a look at similar triangles. So that would be these two questions here. Okay. All right. All right, so for these two problems, okay, the idea here is that we're going to use the fact that the triangles are similar. And it tells us they're similar. So taking a look at them, what I'm noticing is this large triangle, okay, I'm going to take this one and just flip it horizontally so that you get it lined up in a similar way. So it would look something like that if I turned it around, where the 9 is here, the 41 is there, and the 40 is there. So what we could do is set up a proportion. If the triangles are similar, we know that the corresponding sides have to be in the same ratio, making them proportional. So I want to know this x. I really have more information than I need. What I can do is take x and set up the ratio x to 9. So that side to its corresponding side in the other triangle would equal, and then I would go back to the big triangle since x was from the big triangle and say something like 80 over 40. Now notice that 80 to 40 is a 2-to-1 ratio. That means all the sides have to be in a 2-to-1 ratio. This one's hard to see now. I'm going to erase it and put the 9 on there again. Okay, so watch when I go and I use the usual process, which is to cross multiply. So multiply 40 times x and 80 times 9, then divide by 40. I wind up getting 18, but notice that 18 is twice 9. So if this is times 2, then that means the 9 to the x would have to be times 2. So I would know that's 18. So the sides are proportional, so on that one, on 4, the answer would be that x would equal 18. Now, on question number 5, you also have similar triangles. It's just that they're overlapping triangles. So let's take just that big triangle out, and then let's pull that little triangle out. The right angle is here, okay? This we don't know, that's what we're looking for, but actually in the words they told us that y was 10, so I'm going to put 10 there. Then I know this is 6 and this is 60. So I can do a similar thing. Then I know that x to 10, that ratio, should be the same as 60 to 6. So if I do the cross multiplying idea, I would get that 6x would equal 600, and when I divide by 6, I would get x would have to be 100. So this side here has to be 100. I also know that because the numbers were nice and compatible, and I could see that to go from 6 to 60, I would multiply by 10. So that means since the sides have to be proportional, that I would have to multiply by 10 to get side x. So what I know is that that tree must be 100 feet tall. Right. I'm now going to do the special right triangles. So let me take a picture of that. All right, now special right triangles. This is kind of something that a 30, 60, 90 triangle is a type of triangle that is similar to every other 30, 60, 90 triangle. So there's a lot of ways to approach how to solve these kinds of things. When you do this a lot, what I know is that a 30, 60 triangle, the sides of a 30, 60, 90 triangle are in the ratio of 1 to 2, short side to long side, and the middle side would be square root of 3, always. So one way you could do this would be to use similar triangles and to think how the short side would be 1, the long side would be 2, and the 60 degree, the side opposite the 60 degree side, that would be 90. And then what you could do is set up some proportions. So if I'm looking for x, that's the short side, then I know that x to 1, so x to the short side of the 1, 2 square root of 3 triangle would have to equal the side I know, which is 20, to 2. So x would have to equal 10. Notice that makes the short side half the long side, and that's what you're really being told when you see this, that these sides are in the ratio. Let me erase that and write it differently. When you're told that see how the long side is twice the short side. That's always going to be the case. So if I know the long side is 20, I know the short side had to be 10. So if that makes sense to you, feel free to use that idea. And then once I know that that's exactly 10, and if I needed y, I've got several options now. I have more information than I need, but one thing I could do is that y to the square root of 3, because those are corresponding sides, should equal, so y to the square root of 3, since these are corresponding sides, should equal 10 to 1, or I could have said 20, or I could have said 20 to 2. And then when I cross multiply, do you see how we get y equals 10 times the square root of 3? Now that would be actually the best answer in some respects because it would be exact, but it's hard to know how big that is. So we typically would go on and do a decimal and say that's about 17.3. So y is about 17.3. We don't have units on that, so all we can say is 17.3. So that might be a good way to think about it, to connect it back to the similar triangle idea. All right, now 45, 45, 90 degree triangles. If it's a 45, 45, 90, they're always in the ratio 1, 1 to the square root of 2. So that means these two sides that are opposite the 45 degree angles, these two here, they're always the same. Whatever one is, the other one is the same. So 1 to 1. And then the hypotenuse would be square root of 2 as compared. You would multiply by the square root of 2 to get the hypotenuse. So if you're trying to do a problem like this and you wanted your x, you could say x to 1 equals 7 to the square root of 2. And you could cross multiply, but when you do, it's kind of interesting because you'll just get back to where we were. We would get that square root of 2x would be 7, so aren't we just going to get back to, really? So x over 1 really was x, so we really had our answer at that point. Now 7 over the square root of 2 is not typically an acceptable final answer. If you've ever done radicals, not in our class, but in any other class, you may have learned to rationalize the denominator. So you'll a lot of times see the exact answer given to you this way, but we're not dealing with radicals, so we'll actually just take 7 and divide by the square root of 7 divided by the square root of 2 to get an answer, and what we'd find out is that that's about 4.9. So this side is about 4.9. Now we could do a similar thing for y, but don't we know that the two shorter sides have to be the same? So once we find one, we know the other one is 4.9 as well. Now you could also have set that one up. Since x and y are always the same, since these two sides and a 45, 45, 90 would have to be the same. You actually could have done a Pythagorean theorem concept to get that 2 of those x squareds would have to equal 7 squared. So x squared would equal 7 squared divided by 2, and you could do the square root of that. And if you simplified that, the square root of 7 squared is 7. You'd get the same thing. You could put it in your calculator and get that 4.9. So sometimes there's a workaround to those special right triangles. But if you've developed a little bit of number sense, you can, on these kinds of problems, the idea should be, since we know that, they really expect us just to be able to look at the triangle and say, okay, so if I know this side is 7 and I need this one, then I should be able to take 7 divided by the square root of 2 and just be done with it. And then if I know that, then I know this other side also. That's what they really intend for us to do. But I just think that sometimes we struggle with that kind of reasoning. And then on this problem, similar thing. On this one, what they kind of intend for you to do, the way you really use these, once you get a hang of it, is you say to yourself, I know that the ratios of the sides in a 30, 60, 90 are 1 to the square root of 3 to 2. So then you compare and you say, okay, so they should be like this, right? So if the long side is 20, the short side should be half that. So I know the short side should be 10. So if this is 20, the short side should be 10. And then I know going from x to y, I should multiply by the square root of 3. So that's the intent about how to do it. But similar triangles might be a way to do it that would connect with what you did earlier.